Welcome to Digital Logic Design. Throughout this lecture, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. For a function of n variables, the product term in which each of the n variables appear once is called a minterm. The variables may appear in a minterm either in uncomplemented or complemented form. So for a given row of the truth table, the minterm is formed by including the variable x if x equal to 1 and by including x bar or x naught if x equal to 0. So to illustrate this concept, consider this truth table here. So this truth table has 3 input variables. So we have numbered the rows of the truth table from 0 to 7 so that we can refer to them easily. To the row numbers are chosen so that the number represented by the bit patterns here of variables x1 and x2 and x3 reflect the row index. So this figure shows all the minterms of a 3-variable truth table. So a 3-variable so there is one minterm for each row corresponding to the truth table. So, for example, in the first row, the variables have the value x1 equals to 0, x2 equals to 0, and x3 equals to 0, which leads to minterm x1 naught, x2 naught, and x3 naught. In the second row, x1 equal to 0, x2 equal to 0, but x3 equal to 1, which leads to minterm x1 naught, x2 naught, and x3, and so on. So to be able to refer to the individual minterms easily, it is convenient to identify each minterm by an index that corresponds to the row numbers shown in the figure. So we will call the minterm of 0th row M0, the minterm of 1th row M1, and so on. And the minterm of the 7th row is M7. So to write a minterm, let's say for M3, we first write the product variables x1, x2, and x3. Then we observe the binary representation of the index. So M3 is the minterm of the 3rd row. So the binary representation of 3 is 0, 1, and 1. So we only complement the variables which are 0. So x1 is 0 in this row, which means we complement just x1 and we leave x2 and x3 unchanged. So that is the key piece of information to remember to write minterm. We complement the variables if they are 0 in that row. So for instance, in this row, x2 is 0, x1 and x3 are 1, so we have complemented x2 here in the expression of minterm. Why do we do this? We are taking, we are writing the minterm or this product term or this AND term such that the value of this minterm is equal to 1. So if we AND this 1, and in this row, if we AND x1, x2, and x3, it becomes 0 unless we make x2 equal to 1. That is, we complement it. So that's the idea. So in other words, we're trying to set the minterm value equal to 1. Okay, so what are minterms good for? So a function, a logic expression or function can be represented by an expression that is a sum of minterms, where each minterm is ANDed with the values of the function for the corresponding input variables. So this expression leads to an expression which is called sum of product SOP expression, which converts a truth table to a Boolean expression. So minterms are used to synthesize a truth table into a logic circuit. And the cost of a logic circuit, so this is the formula to compute the cost of a logic circuit. So the cost of a logic circuit is equal to the total number of gates used in the design plus the total number of inputs to all gates in the circuit. So I'll now illustrate how to write a sum of product or SOP expression with an example. So let's say we're trying to synthesize this truth table. So this is two variables, x1 and x2, and this is the output of the function. By synthesizing, I mean I want to determine the logic expression corresponding to this truth table, and then I'll design the circuit. So basically we're trying to convert this truth table into a digital circuit, and this process is called synthesis. Okay, at first I notice the rows for which the output of the function is 1. So for the 0th row the output of the function is 1, for the 1th row the output of the function is 1, and for the 2th row, for the 3rd row here, the output of the function is 1. So we only take minterms of the rows for which the function is equal to 1. So we'll only take m0, m1, and m3. So it can be written in a compact format, something like this. So this sigma sign indicates the logical sum operation. So this is basically, we can write this function as f of x1, x2 is equal to m0 plus m1 plus m3, where the plus means the OR operation. So that is why it's called the sum of product, because we're basically summing the minterms to write the expression of f. So this is also another alternative notation. We can just take the m out and just write the row indices inside the parenthesis. So but that's not the end of the story. So what we need to do, if we expand this sum, we get this equation. So you don't need to write this. I mean, you don't need to write the minterm for which the function output is 0. Even if you write it, it's fine, because it's going to get cancelled out, because m2 and 0 is equal to 0, and we know x plus 0 is equal to x. So we end up with only minterms of m0, m1, and m3. If we then write the minterms, we end up with the logic expression of f. So there you go, we have converted a truth table into a logic expression, and now we can implement it in a circuit. So here we have attempted to convert the truth table to a logic expression called synthesis by writing the minterms of each f equal to 1 rows and then summing or ORing them. In other words, we synthesize the function f by considering rows in the truth table for which f is equal to 1. So we only write the minterms corresponding to the rows for which the function is equal to 1. And then we just sum them to obtain the expression. So now that we have an expression, we can easily build a circuit. So our synthesis procedure is complete. So the design on the left here is an implementation of the truth table, but it's not the minimum cost one. Using Boolean Algebra's axioms and theorems, we can further reduce the size of the logic expression above. So by reducing the size of the expression, we're also reducing the cost of implementing the circuit. Because you know this logic gates cost more. So if you can reduce their number, you can also reduce the cost of implementation of the circuit. So the implementation with the minimum cost is called the minimum cost implementation of the circuit, or the truth table. So how do we determine the minimum cost implementation, given that we have the truth table? So after writing the expression of the truth table, we just don't stop there. What we do is that we apply Boolean algebra as long as we can in order to arrive at a smaller expression and therefore a smaller circuit. So this expression x2 plus x1 naught also implements the truth table that I just showed earlier. Look how small the circuit is now. And what is the cost of the circuit? The circuit has 2 gates, 1, 2, and number of inputs to gates is 1, 2, and 3. So the cost of this circuit is only 5. So if we apply Boolean algebra in the original expression, So this is basically the sum of the minterms. So this is minterm 0, this is minterm 3, this is minterm, I think, 2. Sorry, this is minterm 1. So this is just the sum of the minterms. So if we apply Boolean algebras, axioms, and theorems, we can reduce the size of the expression and therefore end up with a smaller circuit and more cost-efficient circuit. So here, for instance, I have just copied this term x1 not x2 here, because as we know, x plus x is equal to x, which means you can write any term of an expression as many times as you want, because x plus x is equal to x. Now what we did here is that we perform commutative operation, and then we perform distributive operation here to obtain x1 plus x1 bar, which is equal to 1, and then we know x and 1 is equal to x, so we end up with x2 plus x1 bar. If you do a cost comparison with the circuit that we derived earlier without applying Boolean algebra and with applying Boolean algebra, we see that there is a massive reduction in cost. The original circuit costed 17. The cost of the original circuit was 17. The one that we did not apply Boolean algebra for, and after applying Boolean algebra, the cost is much lower here. Okay, so hopefully you have a clear idea how to do minimum cost implementation when we're doing synthesis. So please pause this video and try to solve this problem, and then we'll match our answers. So please pause this video. So hopefully you've been able to synthesize the circuit. So we end up with this expression ultimately, x2 naught x3 plus x1 x3 naught. Even if we try to apply Boolean algebra, we cannot further reduce the size of the circuit, so we stop here. And these are the minterms. I've only taken the minterms for which the function output is 1, so we should take minterm 1, minterm 4, minterm 5, and minterm 6. So this is 1, 4, 5, and 6. And this is the implementation of the circuit. And the cost of the circuit is 13, because number of gates is 1, 2, 3, 4, 5, and number of inputs to gates is 1, 2, 3, 4, 5, 6, 7, 8. Okay, minterms are a good way to synthesize a circuit using a sum of product expressions, but there is another way of doing it. So the principle of duality suggests that if it is possible to synthesize a circuit f by considering the rows in the truth table for which f is equal to 1, then it should also be possible to synthesize f by considering the rows for which f is equal to 0. So this gives us an alternative way to design digital logic circuits by using the complements of the minterms, which are called the Maxterms. So the Maxterms are the complements of the minterms. So the Maxterms of a 3-variable truth table is shown here. So minterms are written with smaller m's, and Maxterms are written with capitalized m's. So please pause this video and try to show that M3 here is equal to not M3 by applying De Morgan's theorem, by applying 3-variable De Morgan's theorem. So please pause this video and try to show that capital M3 is equal to not M3, not small m3. So hopefully you've been able to verify that by yourself, that the Maxterms are basically the not version of the minterms and vice versa. So if you just complement M3, small m3, you end up with capital M3. Or if you just complement capital M3, you end up with the minterm. We end up with the corresponding rows minterm. So similar to minterms, if we consider a binary number formed by the values of the input, we can obtain the index of the Maxterms by converting the binary number to decimal number. So the Maxterm index, just like the minterm index, is the exact same as the row index. So the row index, the number formed by the decimal number formed by these 3 digits, and the index of the minterm and the index of the maxterm all are same thing basically. So how do we write a maxterm? So to write a maxterm, capital M3, we first write the sum of the 3 variables. So this is a 3 variable maxterm, 3 variable truth table, so we write x1 plus x2 plus x3. Then we observe the binary representation of the index. Let's say for this row M3, we observe the binary representation of the index. So if we convert 3 to binary, we get 0, 1, and 1. So what we do next is that we complement the variables which are equal to 1 in the binary representation of the index. So 0, 1, 1, here x2 is 1, x3 is also 1. So I have complemented x2 not here, x2 and x3. So the maxterm for the row 3, M3 is equal to x1 plus x2 bar plus x3 bar. So here, this is basically quite opposite to Minterms, where we were trying to set the complements such that the whole thing is equal to 1, whereas in Maxterm we're trying to set the complements such that the whole thing sums to 0. In other words, we're trying to set the Maxterm value equal to 0. So if you put 0 plus 1 complement, if you put the values of x1, x2, and x3 for this row, in this equation you get to 0. So that's how you're trying to set it up. So in Minterm, each of the minterm, we're trying to set up the minterm such that each of these minterm is equal to 1, whereas for Maxterm we're trying to set up the Maxterm such that it is equal to 0. So hopefully you have a clear idea how to write the Maxterms. So a logic expression consisting of the sum terms that are factors of a logical product is said to be the product of sum form. So Minterm was sum of product, and Maxterm is the sort of reverse thing. Maxterm is product of sum. So if each sum is a Maxterm, then the expression is called the product of sum expression for the given function, and it is written something like this. So just like Minterm, so this notation is similar to Minterm, except in Minterm we're summing the thing. Here this symbol indicates that we're basically multiplying each of these Maxterms. So in Minterm you are summing the Minterms, but for Maxterms you are multiplying the Maxterms. So the bottom line is that truth table can be synthesized into a logic circuit using 2 ways: sum of product and product of sum. Okay, now please pause this video and try to synthesize this truth table using product of sum or Maxterms, and then we'll match our answers. So hopefully you've reached this expression. The rest of the procedure for Maxterm is the same as the Minterm. Once you've multiplied all the Maxterms, then you apply Boolean Algebra to further reduce the size of the expression, and once you cannot go any further, you stop there and you say that, okay, this is our final minimum cost product of sum implementation of the truth table. So for instance, after applying Boolean Algebra, we end up with this expression: x1 plus x3, x2 bar plus x3 bar, and we cannot reduce these Maxterms any further, or this expression in fact any further, by applying Boolean Algebra, so we say that this is the minimum cost expression. Okay, so I basically implemented the same truth table using sum of product realization or using Minterms, and in figure B here using product of sum realization, which uses the Maxterms. So which one has the higher cost? So the cost of the product of sum is 1, 2, 3, 4, 5. This is 5 inputs, and number of inputs to gates is 1, 2, 3, 4, 5, 6, 7, 8. So the cost of the circuit in figure A is 13, and the cost of the circuit in figure B is 1, 2, 3, 4, 5, and number of inputs to gate is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they're the same cost. So, but this will not always be the case. So for some circuits, SOP cost might be higher. For other circuits, the product of sum POS cost will be higher. So there is no like set rule that okay, the sum of product will always be higher cost or lower cost. So yeah, so for some circuits, SOP, the cost of SOP could be lower. For other circuits, the cost of POS could be lower. So far we have learned how to synthesize a logic circuit using NOT, AND, and OR gates. So NAND and NOR gates are basically obtained by complementing the outputs of AND and OR gates respectively. Now, building a circuit using NAND and NOR is more attractive because they're implemented with simpler electronic circuits. So NAND and NOR are actually better in terms of implementation than NOT, AND, or OR. So here's the symbol of a 2-input NAND gate. So it's basically the exact same symbol as AND gate, except there is a bubble here. This bubble indicates NOT operation. So the AND output is passed through a NOT gate, and this is indicated by this bubble here. So the only difference with the symbol of AND is this bubble, and this bubble indicates the NOT operation. Similarly, the only difference between the NOR and OR gates is that there is a bubble towards the end of the NOR gate, and this bubble indicates the NOT operation. And this is the multi-input version of the NAND gate and NOR gate. So far we have seen that any logic function can be implemented using sum of product or product of sum form, which leads to logic network that have either an AND and OR structure or an AND structure. So for sum of product, you have an array of AND gates followed by a 1 OR gate. And for product of sum, you have an array of OR gates followed by an AND gate. So now we ask, can we implement any logic expression using NAND or NOR gates instead of AND or OR gates? Because as we just discussed in the earlier slide, that NAND and NOR gates are easier to implement than AND or OR gates. So the idea of NAND or NOR implementation is that we'll first design the circuit using AND and OR gates, and then we'll convert each of the gates in our design into a NAND or NOR gate using De Morgan's theorem. So for that, we need to understand how De Morgan's theorem works at first. So in figure A here, in these three networks, this is just a visual illustration of the De Morgan's theorem here. x1, x2 whole naught is equal to x1 naught plus x2 naught. So this figure here, the NAND gate basically implements the left-hand side of this expression or equation. So just match it, x1, x2 whole naught. So this is actually doing the same thing, x1, x2 whole naught. And this circuit here is implemented the right-hand side of the De Morgan's theorem. So this is x1 naught plus, so this is the OR gate, so that's why it represents this plus, and x1 naught plus x2 naught. Okay, so again we can, and what I've done here, I've just modified the figure and replace these NOT gate symbols with bubbles. So here is a bubble, this indicates a NOT operation, here is another bubble that indicates this NOT operation. So this figure is the same, and they both represent the right hand side of the De Morgan's theorem. But the critical part is that what De Morgan's theorem is telling us, that we can replace this NAND gate with an OR gate with two complemented inputs, and vice versa. So if we have an OR gate with two complemented inputs, this can be replaced by a NAND gate. This is the key piece of information you need to remember. An OR gate with two complemented inputs can be replaced by a NAND gate. An OR gate with two complemented inputs can be replaced by a NAND gate, and vice versa. So this is the other De Morgan's theorem, the dual one. So the expression in B is the dual one of expression A, and vice versa. So again, if we compare this expression, x1 plus x2 whole naught, this is basically this circuit, the NOR gate here. And if we compare the right hand side of the De Morgan's theorem, x1 naught, x2 naught, x1 naught times x2 naught. So this is basically this circuit. Again, I have replaced the NOT gates with the bubble symbols here. So this circuit and this circuit are basically the exact same thing, except that I've replaced the NOT gates with the bubble symbol. So this circuit is telling us that an AND gate with two complemented inputs can be replaced with a NOR gate. So this is the key piece of information we need to remember, that an AND gate with two complemented inputs can be replaced by a NOR gate, and an OR gate with two complemented inputs can be replaced by a NAND gate. So with this information in mind, we can convert a circuit with AND or OR gates to a circuit that contains only NAND or NOR gates. So let's say we're trying to convert this circuit to that contains only NAND and NOR gates. So what we do here is that we add a bubble here and we add a bubble here. There you go, you've already converted these two into NAND gates. And now that we have added a bubble here, we need to add another bubble to compensate for it, because we know x double naught is equal to x. So if we complement or not a variable twice, we get back the original variable x. So x double naught is equal to x. So that's why if we add a bubble here, we need to add another bubble to compensate for this. Similarly, if we add another bubble here, we need to add a bubble here as well to compensate for this. Wait a minute, this is an OR gate with two complemented inputs. So what can we replace this with? We can replace this with a NAND gate according to De Morgan's theorem. So there you go, this circuit only contains NAND gates, and we've converted a circuit with AND or OR gates into a circuit that contains only NAND or NOR gates. So the main message from De Morgan's law is that an AND gate with all inputs complemented can be replaced with a NOR gate, and an OR gate with all inputs complemented can be replaced with a NAND gate. Now please pause this video and try to convert this circuit to NAND or NOR gates. So please pause this video and then we'll match our answers. So hopefully you've been able to solve this. What we do here, we just add a bubble here and add another bubble here and add two bubbles to the inputs of this AND gates to compensate for it. And an AND gate with all inputs complemented can be replaced with a NOR gate. So we end up with this circuit. So hopefully you learned here that how do we convert a truth table into a logic circuit, and we can convert a circuit with AND or OR gates into NAND or NOR gates. So thank you for your time, and let me know if you have any questions in the comment section.